This is Calculus 1. It's section 5 lecture. And it is this section is really just a continuation of section 3.4. Optimization means finding the best outcome, right? Like the word optimal means the best. So optimization means you are you are creating the best. And we're going to do that using calculus. And the way this is done using calculus is for situations where you want to find like a maximum value or a minimum value, where you want to maximize something or minimize something. And which means you're finding maxima and minima. So this section, it's really just like section 3.3 and 3.4, where you're like finding maxima and minima. But we the difference is that like the functions represent something, and we actually have to find the functions ourselves. That's kind of the hard part, is finding the functions ourselves. But after that, it's just a matter of doing the same thing that we do in 3.3 if you're using the first derivative test, or 3.4 if you're using the second derivative test. So let's just jump into a problem. I like section 3.5 problem number 3 a lot because it kind of talks you through the steps. Numbers 1 and 2, you'll notice, are problems that are straight from section 3.4. So it's kind of like saying this is the same thing as 3.4. It's just once you get to number 3, you're not given the function anymore, and your job is to find the function that you're trying to maximize or minimize. So number 3, it says a box with a square base and open top must have a volume of 442,368 cubic centimeters. We wish to find the dimensions of the box that minimize the amount of material used. First, find a formula for the surface area of the box in terms of only x, the length of one side of the square base. And then hint, use the volume formula to express the height of the box in terms of x. Simplify your formula as much as possible. So your job always is to, with these optimization problems, is to actually find a formula. Like, you start off by finding a formula for whatever you're trying to minimize. And in this case, we're trying to minimize the amount of material used. So, so for your first step, write an equation for the value you need to you're either going to be maximizing something or you're going to be minimizing something. That's the first thing you're going to do. And then after that, it's just like 3.3 or 3.4, where you're asked to find max or min. That's all. So in this case, they really tell us that we need to find a formula for the surface area of the box, right? So yeah, we're finding a formula for the surface area of the box. Because we're trying to minimize the amount of material that's being used. So I'm gonna grab a box. I have a box over here, and I like this box because it has I dropped my stylus. I like this box because it has an open top. So there's a mug in it also. But you see the box. So it has an open top, right? So when I write a formula for the surface area, I'm going to have the bottom, right? And then the 4 sides, 1, 2, 3, 4. So keep that in mind as I write the formula. Just put this box off to the side. So our formula, again, it's going to consist of the bottom of the box and then 4 sides. So my area or surface area, let's just, oh, they're calling it A, right? Big A for surface area. It'll be the area of the bottom plus 4 times the area of the sides. Well, I'll say of each side because there are 4 sides, right? So that's how we're going to get our formula, by figuring out the area of the bottom of the box and then the area of each side. And I know it's 4 times the area of each side, which is kind of different from my box because this box that we're given for this problem, it's different because it actually has a square base, which means that each side will be the same, right? It'll, like, each side will have each side will have, yeah, the same area if they all have the same base and they all have the same height. So let's see, it says, and then one other thing is that it tells us that X represents the length of one side of the square base. So we know that the area of a square is base times height. So, or sorry, it's just the side squared, right? Because you have, like, here, I'm going to draw the square. I'll draw the square to make it clear. So that kind of looks like a square, right? So they're telling us that the base is X, and by definition, a square's sides are all the same. So the area of this thing, that's the area of the bottom, which is the square. That's equal to X squared. X times X, or X squared. So that's what goes here. Area of my bottom is X squared. The bottom of my box, I should say. Area equals X squared. And then we're going to add the area of each side times 4 because there are 4 sides. So we're going to have plus 4 times, and in parentheses, we'll have the area of each side. And and let's just say here, I'm going to draw a side. Let's say that let's say that this is a side of the box. So the base for each side is X, and then the height, let's just call that H. And then we can say the area of each side is base times height, or X times H. And so that's what will go here, X times H. So we have written an equation for the value we need to maximize or minimize. And once you've done that, then you want to do one other thing before you go ahead and maximize or minimize, like find the max or min. I will talk about that as soon as I write this down. So notice that the formula that we have here, X squared plus 4XH, that formula has too many variables in it for us to go through the same process that we did in sections 3.3 or 3.4, whichever process you want to use to find max or min. And so we need to like just have one variable involved here on the right side of the equation. So we just have area as a function of, and they specifically say they want us to have area as a function of X. So this is where we use the other information that we're given, which is that the volume of this box has to be, they tell us, 442,368 cubic centimeters. And for this, we're going to use the formula for volume, which is volume equals length times width times height. So we can say that our volume equals length times width times height. Now, since we have we know the base of our box is a square, we know the length and the width are X and X. And then the height of our box we'll just call H, which I already called the height. So our volume is XXH, or in other words, we can say that our volume is X squared H. I'm gonna write the square, X squared H. So what we have is, since our volume is equal to 442,368, we can say that X squared times H is 442,368. And I'm going to switch over to my iPad now. And I wrote all that stuff down. And so what I'm going to do right now is take this equation that I got by using my volume and solve this for H, so that I can then plug in whatever I get in for this H right here, so that I don't have an H anymore there, and I just have something that involves X. So to get a H by itself here, divide both sides by X squared. These cancel, and I get H equals 442,368 over X squared. And I'm going to take this and I'm going to plug this in here. And let's see what we get. So we get X squared plus 4X times my H, which was the 442,368 over X squared. And notice that we can cancel out an X, right? Because this is like over 1. So we can cancel out an X. And I end up with X squared plus 4 times 442,368 over X, over just 1X. And that's my answer. This is my A of X. But let's see what 4 times 442,368 is. Okay, so I just did this on my calculator and I got this huge number, 1,769,472. But this right here, this is my answer for the first part of the problem, which, notice, we haven't done any calculus yet. We've just created a formula for what it is that we're trying to minimize in this case. So, and that's always going to be your first step, is to create a formula for what you need to minimize. And then after that, everything is the same as section 4.3 when you're trying to find maxes or mins, and 3.3 when finding maxes or mins, and 3.4 when finding maxes or mins. So like I said, everything after that's the same, which notice like once you have your function, if you're trying to find max or min, you have to find the derivative, right? So we'll go ahead and find the derivative, which is what they're asking us to do. So this is kind of like this section, problem 3 in this section. It's asking us to go through, it's telling us what all the steps are, right? So we're going to find our derivative. Recognize that this is x squared plus 1,769,472 times x raised to the power of -1, which will make it easier to find our derivative as 2x minus, because this drops to the front, right? So minus 1,769,472 x raised to the power of -2, which I can rewrite this way. Although I recognize I left out some numbers. This is so gigantic. That's why I left out numbers. 1,769,472 there. So that's our second, that's what we're doing next. We just found the derivative, and we're finding the derivative so that we can find the critical numbers, right? So 2x minus 1,769,472 over x squared. Next, calculate when the derivative equals 0. So we're finding the critical numbers, right? And just notice for this one, like, when you find critical numbers, you're finding out when your derivative equals 0, and you're finding when your derivative does not exist. The thing is, our derivative does not exist when the denominator is equal to 0. So when x squared equals 0, which means when x equals 0. But notice, 0 is not in the domain of the original function. So like if you go to the original function, this right here, at x equals 0, a of x is not defined. So so we have an asymptote right there, right? Vertical asymptote. So the x equals 0 is not really a possibility for giving us a minimum, which is what we're looking for. And again, since x, like if you think back to, so these problems, like your variables represent something. And in this case, x represented like the length of the side of the square or something, right? X was like the side of the square. So like it can't be 0. You can't make a box without a side, right? So x can't be 0. It wouldn't make sense. So that's why they're saying just fine, just worry about finding the finding out when the derivative is equal to 0. So we set this equal to 0. Then we're going to solve for x. And anytime you have an equation with fraction in it, you can get rid of that fraction by multiplying both sides by the denominator. So I'm going to multiply both sides by x squared. Distribute this. And I end up with 2x cubed minus x squared times this 1,769,472 over x squared equals 0. So these cancel. Like that's why we multiply by the denominator, to cancel it out. And so we end up with just 2x cubed minus 1,769,472. And then I'll just add this to both sides. And I get 2x cubed equals 1,700,000. This number is so big. Okay, and then I'll divide both sides by 2. Right, I'm trying to get x by itself. So I get x cubed equals, and then figure out what that is. So I ended up with 884,736, and then I'll take the cube root of both sides. And let's see what we get. I wonder if we'll get a nice number. I don't know. Let's see. So we're taking the cubed root of 884,736. Oh my goodness, we got a nice number. Isn't that nice? So we got 96. So here we get x equals 96. And that is what gets to go here. So, and then they're asking us to use the second derivative test here, which is nice because it gives us more practice, right? With the second derivative test. So, second derivative test says if you have a critical number, which we have, 96, then plug that into the second derivative to see if you have a max or a min. So we're gonna go back to our functions derivative in order to find the first derivative. I'm sorry, in order to find the second derivative. So our first derivative was this right here. Or actually, I'm going to use this form right here because we're going to find the second derivative and it's easier to find it in that form. So we'll have so previously we had a prime of x is 2x minus that horrid number. Goodness. Times x raised to the power of -2. And now to find the second derivative, we'll have a double prime of x equals 2. And then this comes down to the front. And then we'll have, well, whatever that is. So I'll pull out the calculator. Let's see what that is. Oh my goodness. Okay, so I multiplied 2 times that number and I got 3,538,944x. And then using the power rule, I subtracted 1 from the -2 to get -3 here. And so this, I'm just going to rewrite this like this as 2 plus 3,538,944 over x cubed. And the second derivative test says to plug in your critical number. So my critical number was this 96. So I'm going to plug this 96 in for my x. So I'll have a double prime of 96 equals 2 plus 3,538,944 over 96 cubed. And because I know this is a positive number, I can say that I have a min right here. Because according to the second derivative test, so just going back to the previous section, all right, second derivative test, here we are. Whenever f double prime of your critical number is positive, then you have a local min. So that's how I know I have a local min, because my second derivative at 96 was a positive number. Now, I don't remember if the homework, if they want us to actually say what the number is. They don't want us to say what, I mean, they do, but I'm just going to put the number in here. As it is. If I hope I typed everything in correctly. Did I? Oh, maybe it looks like, oh, what did I do? 538,944 over 96 cubed. Let's see. Let's see if they wanted the number. Oh no, 3538944 over 96 cubed. Okay, we get 6. I can't believe that's just 6. Oh, why does it say it's wrong still? Let's use the second derivative test. Find, oh, sorry, I'm sorry. That 6 goes here. Right here, they wanted the second derivative. So I'll say 2 plus 353, 3,538,944 over x cubed. Okay, so now it's happy. I was putting this number in the wrong place. So I bet you they would have let me put this form in here. I bet you. I bet you. If I, just replace the x with a 6. But the point is, it says, since your last answer is positive, this means that the graph is concave up, which means that at the 6, we have a local, I'm sorry, at the x equals 96, we have a local min. And then it says your boss is happy now. The idea is that you are creating this box. And you've created the box that will give you the smallest surface area. So so that's really the idea with all of these problems. Again, the hard part is finding the formula basically for like whatever you're trying to maximize or minimize. Let's look at one of the ones involving demand. Let's look at number 13 because it has a cute picture. So it says a dog food producer. This is for the business students. A dog food producer reduced the price of a dog food. With the price at $11, the average monthly sale has been $27,000. And then when the price dropped to $9, the average monthly sales rose to $33,000. Says, assume that monthly sales is linearly related to the price. And the question is, what price would maximize revenue? So in order to find revenue, you have to find something that's called demand, a demand function. And the demand function is, it basically represents price. If you want to sell X items. So like if I want to sell X items, the demand function tells me what price I need to sell them at to sell that number of items. So with these business functions where you're dealing with demand, where you're dealing with revenue, where you're dealing with cost, where you're dealing with profits, you're going to think of your X as the number of items that you're selling, whether it be bags of dog food or tickets or books or t-shirts or meetings with a client, like whatever you're selling. And then little p of x represents, well, I already wrote what that represents. That's the price to sell X items. And revenue, it's basically defined as the number of items times the price for each item. That's how revenue is defined. For example, let's say we're selling math t-shirts on Laney's campus and we're selling them each for $10. And our first day selling our t-shirts, let's say that 5 people buy our t-shirts for $10. Then our revenue would be 5 times 10 or $50. So there's actually a formula for revenue, and it's R of X equals X. So that's the number of items times P of X, which is the demand function. That's the price to sell X items. So number of items times price. There's the formula for revenue. And that's what we need to, that's what we need to get in order to maximize our revenue. So we'll do that right now. And in order to do that, first, we need to find our demand function, because as you see, the revenue includes the demand function in it. So we're going to first focus on finding the demand function. And we'll do that by using the information that we're given here, that when the price is $11, we're selling 27,000 bags of dog food. So this is an ordered pair looking like this. 27,000, that's the number of items, and then 11 is the price, and that's why. And then notice that you have another ordered pair that you're given here. When your price is $9, the sales are, you end up selling 33,000 bags. So you have another ordered pair, this 33,000, and then the price, $9. So I'm going to write those down, and I'll switch over to the iPad. And basically what we're going to do to find the demand function is we're going to find the equation of the line that has these 2 points, because it says right here that monthly sales, assume that monthly sales is linearly related to the price. So they're saying the demand function is going to be the equation of a line. And so we're going to find the equation of the line. So I'm switching over to iPad. All right, so I wrote the points down, and what we're doing right now is we're finding our P of X, our demand function, which means we're going to find the equation of the line. And let's use the slope formula. So our slope M is 9 minus 11 over 33,000 minus 27,000, which ends up giving us -2 over 6,000. Is that right? I think that's right. So that's -1 over 3,000. That reduces to -1 over 3,000. So that's the slope of our line. And then let's use y equals mx plus b. And you can pick either point. I'll just use the first point. So I'll have 11 equals my m, which is -1 over 3,000, times my x, 27,000, plus b. And I'm trying to find b now. So I have 11 equals 3,000 goes into 27,000 9 times. So this ends up being -9 plus b. I think that's right. That's so nice, isn't it? And then from here, I'll just add 9 to both sides to get my b. So I end up with b equals 11 plus 9, which is 20. So my demand function is P of X, so that's my Y, equals my M, which is -1 over 3,000, X plus my B, which was 20. That's my demand function. We were asked in the problem asked us to maximize revenue. And the revenue formula is this right here. I wrote it in the corner of the page. R of X equals X times P of X. So I'm going to use what I just found, my demand function, and I'm going to use that to find a function for my revenue. in order to maximize it. So this is like all of the work, I feel like, for these problems, not all the work, but a lot of the work is just finding the formula that you're trying to maximize or minimize. In this case, we want to maximize revenue. So we will have, again, R of X equals X times P of X. And our P of X we just found is this right here. So I'm going to replace that P of X with negative 1 over 3,000 X plus 20. And this is my formula for revenue, my formula for what I want to maximize. So I'm going to distribute this X here. So I get R of X is negative 1 over 3,000 X squared plus 20X. And then, and now I'm going to maximize this. So I'm going to go through my process of finding my derivative. So I'm trying to find a maximum. So I'm finding my derivative. So power rule. So I have negative 2 over 3,000 X plus derivative of 20X is just 20. And then I have to find out when my derivative is equal to 0 and when it does not exist, but it exists everywhere because I don't have a denominator that can be 0. So I don't have to worry about this part. I just have to worry about equals 0. So I take my negative 2 over 3,000 X plus 20, set that equal to 0. I can get rid of my fraction here by multiplying both sides by 3,000. This gets distributed, and I'm left with just negative 2x plus 3,000 times 20. That's 60,000. Is that right? Yes, equals 0. And then let's just move this 2x to the other side. So I have 60,000 equals 2x, and then I'll divide both sides by 2. That's to find out what my x is. And I get 30,000 equals x. This is my only critical number. Now, let me just say, for a lot of these problems, you're going to end up with just one critical number and it's going to work. So you don't really have to do what I'm about to do. If you have just one critical number, it's going to work. But if you want to check to make sure that this gives you what we want, what do we want? We want to maximize the revenue. Find the second derivative. I found the first derivative is this. So the second derivative is really easy because derivative of 20 is just 0. And then I have just negative 2 over 3,000. So my second derivative is just negative 2 over 3,000, which is always negative. So if I like plug in my 30,000 for X, I don't even have anything to plug in. I mean, any place to plug it in. So this is negative, which according to the second derivative test tells us that we have a max right here. So when your second derivative of your critical number is negative, you have a max, which is what we wanted. So notice it works. We were trying to maximize revenue. So oftentimes, like, you get just one critical number and it just works. So you don't really have to do what I just did. So this 30,000 represents the number of items that we need to sell to maximize revenue. Number of items to maximize revenue. I guess in this case, it's number of bags of dog food, right? To maximize our revenue. But then if you like go back to the problem, notice the problem doesn't really ask us for the number of items that would maximize our revenue. The problem is asking us for the price that would maximize our revenue. So what we have to do is take our number of items and plug them into our formula that we had for the price, which was the demand function, because the demand represents price. That's this right here. So I'm just going to write that again, that our price is the demand function, P of X. This is demand function, P of X. And in this case, that's equal to negative something. I forget, negative 1 over 3,000 x plus 20. And so our job, since we found the number of items that we need to sell to maximize our revenue, now, in order to find out the price that we need to sell those items for, in order to be able to actually sell that number of items, we need to plug that in, that 30,000 in for X. So I'll have P of 30,000 equals negative 1 over 3,000. I love these numbers this time, times 30,000 plus 20. And I end up with, okay, I said I love these numbers and I do. It's just, it's like all these zeros are just kind of, okay, 30 over 3. I can handle that. That's negative 10 plus 20, which is $10. That's the amount of money we have to sell this dog food for. $10 a bag. So just a reminder, P of X represents, little p of X represents demand. This is where P is the price and X is the number of items. Number of items. P of X represents the price. And then R of X is the revenue. And R of X is equal to X times P of X, little p of X. And then one other formula that's going to come up for you is the profit, which this problem didn't have, but some other problems have. Profit is defined as revenue. It's basically the amount of money that you take in minus the cost that you had to pay to produce whatever it is that you're selling. So usually a big P is used for profit, and we say that's equal to R of X minus C of X. So I'll make another video that involves profit, just so you have one to go by. But anyway, in the meantime, try these and good luck trying them. Oh, you know what? I never entered my answer just to make sure this is correct. So let me enter the answer. Nice $10. Yay, the numbers were so nice here. Take care, everybody. Bye.